Hello, can you see the slide?
Yes, sir, it is visible.
Okay. Okay, so last lecture we saw two new definitions. One was the extinction coefficient, and the extinction coefficient is a multiplication of uh, extinction cross section multiplied by the concentration. Okay, you can write in terms of the, so you can have a cross section in terms of the mass, centimeter square per unit mass, or you can have a cross section centimeter square per unit per molecule. You can also have one more unit we are not discussed in the last lecture is you can have a cross section per unit volume. Anyway, but if you multiply this concentration and these things, you get a quantity that is called extinction coefficient. And the unit of extinction coefficients are per meter or per kilometer, whatever, I mean, per distance. So that way you are kind of in a relief from the worrying about the concentrations and the individual property of the molecule or the material. This is so. Suppose you are a chemistry person, probably you want to know the concentrations, or probably you want to find out the kind of an cross sections and so on. But if you are not say chemistry person, but you are doing the radiative transfer some other person for astronomy or for energy calculations or something, you are really don't want to. You are not really interested into finding out this. Cross section and concentrations. What you want to know is that how much radiation is reduced, and if you substitute instead of cross section, if you substitute beta, that we call it extinction coefficient, then it makes your life little easier. Okay. And one of the property of the extinction coefficient, even extinction cross section, was that there can be so scattering and absorption can be separately treated and can be just simply added. Same is true for the extinction coefficient. Okay. Then we also looked into the kind of an it's a practical application. One of the practical application of the extinction coefficient is to finding out the visibility into the atmosphere. And then there is an instrument called nephelometer that provides you scattering coefficient. So if you assume that there is no absorption, just in scattering, you can probably calculate extinction. So your extinction coefficient is same as a scattering coefficient, and from that you can find out how far you can see into the atmosphere. And what we wanted to do last time is use the real values that is found into the uh, uh, the real values that are being observed over the Ahmedabad, and see that how far you can see over Ahmedabad. I asked you last time to provide you. I mean, I asked Tejas to provide you some values. Did you people get some values to work on? Last time Heath contacted me, and
Yes, sir.
yeah, Heath.
Sir, we get some values from sir.
So you remember what was the values? And then I also wanted the values for the without aerosols, just for the air molecules. So what are those values, and what are the values with aerosols and with all the pollutions into the atmosphere?
Sir, I have done a calculation and I have sent that Excel file to you.
Yeah, you have sent me Excel file. I just want to know all the other people's whether they also done that or not. So just I wanted to know how many of you actually just somehow. Okay. So I mean, can you, do you remember the, so Heath, do you remember what was the typical values?
Sir, yes, 1 second, sir, only 1 second. Sir, it is in the order of 10 to the power minus 6. Sir,
Okay.
my file is opening, so wait, only 1 second.
Anyway, so I tell you what is the typical value. So something with aerosols and all those things, you have values more than 200 into 10 to the power minus 6. Okay. And if you are only talking about the say relay, air molecules and scattering because of the air molecules without any particles, any pollution into the atmosphere, you have a value something around 2 into the 10 to the power minus 6. So something like 200 times, 100 times more scattering is happening because of the aerosol particle. That's the one point I wanted to you people to appreciate. And then we also found the equation. Do you remember what was the equation to get the visibility to extinction? Sorry, extinction to the visibility. How many of you remember that? I mean, we actually derived that equation. Some of you actually derived that equation. I hope all of you have done that exercise.
Sir, it was 3.92 divided by scattering coefficient.
Very good. 3.92 divided by the scattering coefficient. And the scattering coefficient, I told you, 210 to the power minus 6 meter. That is for the total with aerosol. So what, how far you can see with this and how far you can see without, I mean, with clean atmosphere, without any aerosols. And without aerosols, you have number 2 into 10 to the power minus 6. Okay, someone has replied on comment. Okay, Danny has given that equation 3.91 divided by B. Okay, and I'm telling you that value of the B is, see, one thing I wanted to kind of forgot to mention about, you have 210 to the power minus 6. So 210 to the power minus 6, if you take it denominator, it is 10 to the power plus 6. And 10 to the power plus 6, how do you pronounce it? We pronounce it as a million. Okay, so like you have a, like when you have a, let's say you are talking about the units of the length, so you can say per meter, you can say per centimeter, you can also sometimes say per kilometer. Similarly, when you have values like 10 to the power minus 6, it will be often mentioned as 200 capital M, small m, inverse minus 1. That means 200 per million meter. That is how it is pronounced. Okay, so extinction coefficient is 200 per million meter for the aerosols with pollutions. Extinction coefficient is 2 per million meter for clean air. So, yeah. Could you get the kilometer from that? And I hope everybody has a calculator available into their phone or at least on your computer. You can just do, I mean, it's simply 3.92 or 3.91 divided by the 200. That's the as simple as that. Okay, Heath has given the answer 19 kilometers. That is for what? With aerosol? Okay. And without aerosol, how far you can see? (1,955 kilometers). That's a very long distance. I have not calculated, but let me try now. But I guess it may be true actually. Okay, I am also getting the similar number. Okay, Heath has given answer something. Okay, I said 942 kilometers for red without aerosol. So Definitely for other wavelength, it should be less than that. And yeah, so if you are taking the 2 10 to the power minus 6, then what the Dani has written is correct. Okay, you have to multiply by so it will be like in thousands of kilometers typically. Okay, so you can appreciate how much the air pollution is actually contributing to the air. Of course, we have not talked about the wavelength dependence actually, but we are kind of trying to find out only for single wavelength and so on. Uh, we have also not talked about how to get the scattering coefficient for the air molecules. So that is what I plan to cover today. Okay. So anyway, so this we have seen. Let me come here. Anyway, this equation we have derived, so no need to go again into the details. Okay, one more definition that we saw was an optical thickness. And what is optical thickness? Optical thickness is an integration of so this is extinction coefficient. K into rho is an extinction coefficient, and it is to kind of integrate over a certain distance, ds or s to s1. That is the optical thickness. Okay, and you can guess from this equation that optical thickness will have no unit. Extinction coefficient has a unit per meter. You may multiply ds, that is a meter unit. So optical thickness is a no unit. Okay. Okay. The equation that you are seeing here, this equation and its solution, it was first derived by the Schwarzschild. Okay, and uh, that's why it's called Schwarzschild equation. Okay. And how do did we derive the solution to this equation? No. Anyway, I think we stopped at optical thickness. So optical thickness is integration of beta, and convention is that optical thickness is kind of as a negative of the beta into ds. Okay. We will come to this convention, why this convention is there. But this, if you remember this thing, what we want to do is that you have an equation of the radiative transfer equation. This is the radiative transfer equation without any scattering, and you have kind of an only emissions because of the black body radiations, and you have absorption as per the Beer-Lambert law, and you have the uh, tau into the denominator. Okay, so this is an equation in terms of the optical thickness, and solution to this equation is the what we wanted to find out. And how do we find out the solution of this equation? So what I'm trying to do is that I have bought new kind of an writing pad that can be written on the computer. I will try to write it. I'm not sure how far I will be successful. So just I want to give it try. I mean, you can also do parallelly on your notebook. You can write down this equation: minus di by d tau equal to minus I plus beta plus mass function. Okay, and how do you find the optical thickness? I mean, how do you find the solution to this equation? So what you do is that you multiply this all the terms with e power minus tau, and then integrate from 0 to s1. If you are doing it from top for certain distance. Okay, so let us do that. Let us do that parallelly. I will do onto the computer. Probably you do into your notebook. So let me share you another thing, whiteboard. Okay. I will say start new whiteboard, and okay, so I'm not sure I will. Okay, okay, I'm just trying. I'm not sure how it works, so let me. Okay, so you have to bear with me. Okay, you should be able to see the now whiteboard. Are you able to see the whiteboard?
Yes,
Sir.
sir.
Okay, I'm not sure able I will be able to write it or not, but anyway, let's give it a try. So we had an equation. Okay, it looks very thin. Let me just change the and let me change the color also. Okay. Are you able to see the writing?
Yes, sir.
Okay, there will be a minus sign. I'm just dropping all that brackets because I'm finding it very uncomfortable to write onto this. Okay. Okay. So I multiply e power minus tau s1 and then s. That is an integration from s to s1. That's what I want to integrate here into I. Okay, I think I need some better way of doing it. Okay, I think I am not finding this very comfortable. Let me add some other software. Okay, somebody has written something. Uh, okay, I'm trying another software called Whiteboard. Let me see if it works onto that. Okay, you may be able to see another one. Something has happened. Okay, so let Are you able to see the equation now?
Yes, sir.
Okay.
Yes.
So what I'm trying to do is that take the d tau on to other side. So I have I plus d tau plus beta. Of course, all of these are like equation of uh, the positions and all those things. So I'm just dropping the things. Okay. And then I multiply. So I bring this onto other side. Okay. So now what I have done is that I multiply by e power minus tau. If you look at this term, what is this term? So if you look at this, I can write d, then integration e power minus tau, which is from S1 to S1 into I equal to d e power minus tau S1 to S. Okay. Now you do the integration from both the sides. What do you get? So I say integration 0 to S1, for example. Okay. So of course, I mean this is straightforward. You know the integration, and then there is a differentiation. So you can simply write down this term. Okay. Let me use some other color. Okay. And this I will keep as it is. Sorry, I am forgotten to mention there is a d tau here. There is a d tau here. Okay. So I will write just 0 to S1 e power minus tau S1 to S into d tau. Of course, into B also is there. And here what we are going to get. So we put, when we put S1, when we put S1, there is an there is no integration in terms of the ds. So this term is going to be the 0. So I mean this term is going to be the 0. So e power 0 is 1. So we get an I at S1 minus sorry. Just give me 1 minute. Sorry, I'm back now. Okay, so there is an integration. Okay, 0 to S1 d e d tau. Okay, okay, I think that's it. So this is the kind of a solution. Okay, so let me go back to my slides.
Hello?
Yeah.
Sir, in the second last term, sir, sir, when we put S1 in a limit, sir, you told that that part will be 1.
E raised to minus.
You mean the first term, actually, not the last term.
No, sir,
This term.
second last step.
Second last step, okay. So when we substitute S1 into this here, so you have e power minus tau S1 to S1, okay. So you don't have any physical distance to kind of cover, okay. And if you have so what is the tau actually in this term, okay? The tau is in integration from S to S1, okay. So S1 equal to S1, then you have no physical distance. So what you had b tau equal to K rho into ds or K into n into ds, okay. This is your definition of d tau.
Sir, I understood, sir. Thank you, sir.
Okay. So d tau equal to d tau equal to this is very difficult to work with this pen. Okay. D tau equal to minus beta into ds. So if your ds is 0, then your d tau is also 0. And that is what we have done into this when we substituted S1. Okay. So let me go back to my presentation. Okay, so we are back into this presentation. Okay, did we get this equation or not? I hope we get. Okay. So this is the solution. This is the radiative transfer equation, and this is the solution. And this solution or this radiative transfer equation is known as Schwarzschild's equations, because he was a kind of a genius scientist actually. At the age of 16 or something, he published the paper onto the binary stars and orbits of the binary stars, and he has almost every field of optics he has contributed. Anyway, so for us the interesting part is this solution. Okay, and now let us say so you have this solution, and let us say you are thinking about the radiation. Let's say uh, radiation at top of the atmosphere, okay, coming downward to the earth. Well, if you are doing these things, what would be the typical terms? So at top of the atmosphere, you will not have beta, okay, because I mean above the atmosphere there is no atmosphere, and if there is no atmosphere there is no question of the temperature, and if there is no question, beta is kind of a zero, okay, and then you are kind of doing it like radiation propagating downward. All you will have is this term, and then all the contribution that comes from the part of the atmosphere only. If you are thinking about the say, if you are using this radiative transfer to find out, let's say you have a satellite into the orbit and you want to find out, you are making a measurements from the satellite. Your satellite is looking toward the Earth, and you have to be you have to remember that there will be one extra term here, and that will be because Earth's surface has a temperature, and because of that, it also emits the radiations. Okay, and that radiation will also be attenuated in the similar fashion like I lambda. Okay, so after once you have found this equation, all is all things only things remains to do is that find out the appropriate boundary conditions, and then you apply this boundary condition, and then you get the equations, and that is all ultimately kind of an radiative transfer studies. Okay. Okay, so we have found this equation. Okay, now this equation is a very general equation. If you see when we define the tau, I also warn you that there is one something called optical depth, and that's different from that optical thickness. Optical thickness doesn't have kind of a directional things. It is along the direction of the S. If your beam is propagating in these directions, we are talking about S to S1. Okay. So of course, I mean this is useful. This is a very general equations, but what you want, what most of time you will be doing is you will be dealing with the atmosphere. Okay, and what is the thickness? Okay, so what is the typical thickness of the atmosphere? Do you have an idea up to what altitude you can expect to find the something atmospheric molecules that is significant for the radiative transfer processes? I want to know from you up to what altitude you expect significant atmosphere, so significant number of air molecules.
Sir, from up to 50 to 90 kilometers from Earth's surface, up to tropopause.
Tropopause. So okay, yeah. So tell me, what is the altitude of tropopause?
Sir, probably it's around 90 kilometer. Sir, I don't know. Sorry.
Okay. Anybody else want to give the answer? What is the altitude of tropopause? Are you able to see my slides or not? Because I'm not sure. No.
Yes, sir, it is visible, sir. Your slide
Okay,
is visible.
okay, good. Yeah, so topopause is at 18 kilometer, okay, and about topopause 18 kilometer at the near the equator, and it's about 12 to 13 kilometer, 12 even 10 kilo less than 10 kilometer over the polar regions, okay. So but you can have significant atmosphere above tropopause. In the stratosphere you can have significant atmosphere, but above stratopause do not have much atmosphere. So typically you can think that atmosphere is only up to 100 kilometers. Okay. Now tell me, what is the radius of the Earth?
6,400 kilometers.
6,400 kilometers. Very good. So compared to radius of the Earth, layer of the atmosphere is very small. Okay. So in horizontal directions you have much more uniformity compared to the vertical direction. And even at our experience that even if you go to ocean or very clean, very obstruction free site, you can't see very far distances. You cannot see the curvature of the Earth. So what is more suitable for us or atmospheric application is that we assume that atmosphere is kind of a uniform into the horizontal directions and only the variations vertical direction. Particularly if you want to solve the radiative transfer calculation for us for one particular location or for a small area, okay, this kind of an assumption is very good. So it makes the things much simpler for us. So most of time when you will be dealing with the atmospheric radiative transfer, you will be kind of an assuming plane parallel atmosphere. That means atmosphere has a variations, atmospheric properties varies in the vertical directions. As a function of the vertical directions, how the radiation will vary, but you really don't worry about the horizontal directions, because for small distances you can kind of take it as an homogeneous. Okay, so direction that is into the vertically upward direction. So if you take a Cartesian coordinates or if you take a polar coordinates, the direction of the jet usually take as a vertical direction. It's called zenith direction in technical terms. The angle with respect to this zenith direction is called, we will call it theta. So whenever we use the theta, we are talking about this angle theta. Okay, and when we are using phi, we are talking about this angle phi. Okay, so angle of this plane with respect to the x-axis, that is the phi, and angle with respect to the zenith, that is the theta. Okay. So what you can do is that instead of optical thickness, which is in the, so suppose you are interested in finding the radiation in the direction of S, you can do the calculations in terms of the Z, and then you can simply divide by cos theta, that is mu, and you can get the value. So you will get lots and lots of equation with cos theta. Now that will make it your life difficult. So what you can do is that you can say cos theta is mu. Okay. Then you write this equation in terms of the mu. So now we are defining a new quantity called optical depth. Okay, and optical depth is same as an optical thickness. It is an integration of the extinction coefficient in the direction of the vertical, in the direction of the Z, in the vertical direction. Okay, so we are talking about the integration only into the vertical directions. And if you need to use this quantity into any other directions, we simply divide it by the mu or divided by the cos theta. So that is our radiative transfer equation for the plane parallel atmosphere. So radiative transfer equation in plane parallel atmosphere without any scattering terms will look like this. Okay, so this is the equation. Okay. Now I warn you that most of time you will not be using optical thickness. You will be using the optical depth. Whenever you are reading a literature, there is a word called optical thickness. Be extra careful, because optical thickness is not same thing as an optical depth. Optical thickness can be in any direction, in the direction of the radiation. So it need not be in the direction of the Z. As an optical depth is always into the direction of Z, always in the zenith direction. So most of the time you will be using the optical depth, but once in a while you will come across optical thickness, so you should not confuse that with optical depth. One thing many of you people are using the mode. I don't know how many of you how many of you have heard the satellite called MODIS, MODIS, MODIS?
Yes, sir, I've heard.
Yes, sir.
Okay, so many of you have heard MODIS, and this is very popular satellite with the atmospheric science community. It gives aerosol optical depth. It also provides cloud optical depth and many cloud properties and so on. Okay, now if you look at this literature and look at the definition of the various properties, it calls optical thickness. It's not actually optical thickness, it is an optical depth. So why I'm telling you is that you should not get confused with this thing. So technically or very definition wise, optical depth is the optical thickness is the any direction, whereas an optical depth is in the direction of the jet. But many people use it very loosely, and that leads to a lot of confusion. So again and again, I emphasize that optical depth means the word depth implies that we are talking about from top to downward in a vertical directions. That's the in a kind of one particular directions. That's what it means by the depth. Okay. So if you have optical depth, optical depth is kind of a starting point for most of your radiative transfer calculation. First thing, when you are asked to do a radiative transfer calculations, first thing people will ask you, scientists will ask you that what is the optical depth? Okay, whether it is cloud, whether it's atmosphere, whether it's air molecules or absorption by the gases or scattering by the aerosol particles. So optical depth is kind of a very primary important quantity to calculate the amount of the radiation that we are going to lose or that we are going to gain and so on. Okay. What I want to do is that we see one. Okay, so there are few conventions. So optical depth is taken 0 at top of the atmosphere. Okay, optical depth is taken many times you write it tau star or something. Okay, so as you coming downward into the atmosphere, your optical depth increases. Okay, so suppose somebody says that optical depth of the cloud, it means optical depth of the bottom of the cloud minus optical depth of the top of the cloud. Okay, that is the convention that we use. Okay, another convention that I find very confusing. I don't know why scientists could have easily avoided, but if you go into the literature, Can you hear me now?
Yes, sir.
Sorry, I lost the internet connection in between. So, okay. So what was the last thing you could hear? I was talking about,
So we can see your screen.
you can't see our screen. Okay, let me reconnect the screen. Yeah, can you see it now?
Yes, sir.
Okay. I wonder, I mean, how big you can see my screen? I mean, are you able to see the Google Slides written in the bottom and number 35, or you are able to
Yes,
see
sir.
only white part,
Yes, sir. We
We
are
can
able
see
to.
the whole screen.
including the URL and all those things?
Yes,
Yes.
sir.
Okay, good. No, because if you can see the numbers, you can always tell that we were on the so and so number of the slide. So that's why. Okay. So I was explaining the convention. I hope you. I mean, I was trying to make a point that there is a difference between optical depth and optical thickness, and you should not confuse between these two. But many people, even very experienced scientists and this very well popular data products also, they keep on confusing these things. One example is MODIS. Okay, they call it optical thickness, but actually what they are providing is optical depth. So that was one point I want to try to make. So when it comes to be an quantity, be careful. I mean, it can be confusing, but it is always nice to be the certain. I mean, physical point of view, there is no big difference between optical thickness and optical depth. It is a convention that optical depth is something your radiation will experience when it is going into vertical directions. Optical thickness is something your radiation will experience if it is going into some other directions. And you can always find a relationship between them. Okay, optical depth is simply, you can multiply optical thickness with mu cos theta, and you can get optical depth. Or optical depth is optical thickness divided by mu. Okay, and that's why you get this equation. Okay, and there are some conventions that did we cover the conventions? I mean, I wanted to tell you that of the atmosphere, optical thickness is taken 0. As we come down, it is increasing. Okay, so it is like a reverse way. If you are increasing the jet, your optical d tau will be the decreasing. Okay, so this is for the sign convention. Another convention was regarding mu. Okay, so if you have a so your this direction is always fixed. Okay, this is taken always from surface toward the sky. Okay, positive. So and suppose your radiation is going from surface toward the sky, then this theta is your mu. This theta is kind of an less than 90 degree. Okay, and if you calculate the cos, it will not be it will be the positive number. But suppose you are at top of the atmosphere and your radiation is coming downward like this. Okay, this theta you should take. Okay, should you take the theta with respect to its tail? Should you take the theta when it is gone down and then you draw this arrow downward, or you take the theta from here all the way up to here? I wish I can draw it. Let me try. Is there any way to? Okay, I don't know whether I can draw it, but I hope you are able to get the point. Okay, so let us say if your radiation is going in this direction, for example. Okay, so your theta will start from this angle. Okay, and it can be taken all the way up to this angle in this direction. If you okay, in that case, if you calculate the cos of that theta, you will get a negative number. What you can do is that instead of taking the negative of that large theta, you can always take the theta with respect to its tail and with respect to this direction, and then you can put an additional sign minus mu. So when it is in this case, so convention is that to take always mu with respect to vertical directions and in vertical hemisphere. And if your radiation is propagating downward, you kind of use the minus mu, and if it is radiation is propagating in vertical direction, you just simply use the positive mu. Okay. So with this mu and this theta, let us see one example of okay, this is okay. So if you notice, this is not very different from the previously written equation. Only difference you will see it is here Z. Instead of S, now I am using the term Z to specifically mention that we are talking about the vertical direction and not any other direction. Okay, and dz implies the change into the vertical direction. Okay. And then like optical thickness, optical depth can also be written like this. Okay. Now we have some problem with this term. We have like beta. We already know the extinction efficiency. No, we know the extinction coefficient. Okay, and that is this. That is k into rho. Okay. What we can do is that we can define a new term called extinction efficiency. So what is the K? So K is an scattering cross section or extinction cross section, and if you are talking about a particle, it will also have a physical cross section. So if you take a ratio of that, you can define something called extinction efficiency. So extinction efficiency ratio of optical cross section, that can be absorption cross section or a scattering cross section or extinction cross section, divided by physical cross section of the particle, assuming that particle is a sphere. Okay. Now, why we want to do these things? This is because doing the mathematics with this Q is easier than doing the mathematics with K. Okay, because it allows you to think without thinking. So let us say if you have a say visible wavelength and you are doing the calculations for the scattering cross sections, and you are doing this optical depth calculations, what you will have is that you have to still worry about the particle size, and you will still have to worry about the wavelength. But suppose you have a radio wave and you are doing the ionospheric calculations. Now, what is the typical size of the radio waves? Anybody knows that? What is the typical order of the wavelength of the radio waves? Anybody knows the radio frequency? Anybody listens to the FM radio? Radio
So,
yeah.
so 20 hertz to 200 kilohertz.
Yeah, that is the whole band. But what is the typical frequencies that you see the radio stations? I mean, if you have ever heard the FM radio, whether it is Radio
91.
Mirchi or Radio Ahmedabad or whatever, Radio City
So
or
91.12.
so if you 91 megahertz, and if you calculate the wavelength, you will get some number that will be in terms of the meters. Okay. Now, as far as electromagnetic radiation is concerned, so the radio will not be affected by the air molecules, but it will be affected by the ionosphere. Why? Because ionospheric disturbances are of the size of the wavelength of the radiations. Okay, so that way, this quantity allows you to think about this problem, optical depth problem or scattering problem, without worrying about the wavelength and the size of the scatterer. Okay, that's why we need to define a new quantity. So what this plot shows is that x-axis is size parameter and this axis is scattering efficiency. Okay. Now I hope you are able to see the slides. Okay. Again, there is one new parameter called size parameter now. Okay. So what is the size parameter? So size parameter is a ratio of particle circumference divided by the wavelength. Okay, I hope you are able to read this. It looks very small to my own screen. I don't know how it will look onto the mobile phone. Anyway, so as I mentioned before, the size parameter again allows, so what your scattering depends on to the size parameter, not onto the wavelength. I mean, you might have heard that scattering depends on to the wavelength, lambda power 4 and so on. But that's not entire truth. Okay, the entire truth is that scattering depends on to the ratio of the particle and the wavelength. Okay, so if you are using the same radiations for the particles which are very, very small, scattering will not happen. Okay. Similarly, for example, radio waves, that will not be affected by the air molecules, but they will be affected by the some radiation blow into the ionosphere that is size of the 1 meter. Okay? So size parameter is an important factor. It's a ratio of the circumference divided by wavelength. That is what it depends on to it. Okay. So if you take the size parameter on x-axis, let us say you have a particle of the size 0.5 micrometer or 1 nanometer. That is the 1 nanometer. That is the size of the air molecules. Okay. What is the lambda for visible wavelength? Is something around 0.5 micrometer or 500 nanometers. Okay. So you can keep the particle size same and then go on increasing the wavelength. Your size parameter will go on decreasing. Or you can do the same way. You can keep the wavelength fixed and you can change the size of the particle. Effect will be the same. The point I want to make is this. So if you have a very, very large particle with respect to your wavelength, so your lambda is small and particle size is very large, the x is very large. The extinction efficiency tends to go to a number called, then that number is 2. Why 2? Okay, that is another question. I think you, if you have studied the diffraction, you will know the answer why it is 2. Okay. So what this different curve shows is that if the particle has no absorption, it's purely scattering type of particles, and then let us say if you had an air molecule, so sorry, not, let's say you did an aerosol particle. The aerosol particle will have a size of the 0.5 micrometer, and let us say you are talking, you have green wavelength that also has a 0.5 micrometer. So your extinction ratio will be 1. And now you go on increasing the particle. Okay, let's say you have a particle of the size, say, 1 micrometer. You will have high efficiency, very lot of scattering, almost 5 times scattering. Then this scattering will go on decreasing. Then it will go on increasing. So there will be like these structures as the size of the particles. But eventually, if you take a very, very large particle, so for example, what is the typical size of the cloud droplets? Anyone has idea? Have you seen the raindrops first? How many of you have an idea about the raindrop sizes? Do you have a measurements? Is the pages available into the meeting?
Sir, it's in micron or something?
No, that's not the right answer. First, let us talk about the raindrop sizes. Have you, of course, I mean, everybody experienced the rain, okay? I mean, you can guess what would be the typical size of the rain. If there is a heavy rain, light rain. I mean, Gujarati માં આપણે કહીએ તો મચ્છરિયા, ઘણી વાર મચ્છરિયા આવે, ઘણી વાર ધોધમાર વરસાદ.
Sir, it may be 1 to 2 mm.
1 to 2?
Millimeter, sir?
Yeah, 1 to 2 millimeter. That is the typical size. You can have up to centimeter size of the raindrops, and you can have kind of a half the millimeter size of the raindrops that we call it machariya. Okay. So that is the raindrop. So what do you expect? The size of the cloud droplets will be larger or it will be smaller? You have a rain coming from the cloud. Okay, your raindrops comes from the cloud. So if your raindrop is, yeah, somebody is speaking, yeah.
So I was telling that cloud drops let should be smaller than.
Okay, yeah. So there is no fixed rule that cloud droplet should be smaller than the raindrop. Okay. What happens? But I mean, in most circumstances, that is true. That cloud droplets will be smaller than the rain droplets. Particularly the cloud which is not raining definitely has a smaller droplet size than the raindrop sizes. But if the cloud is raining, it's not necessary that your raindrop size will be larger than the cloud droplet size, because when the rain falls, a raindrop falls from the cloud, that it evaporates and it gets broken up and so on into the because of the atmospheric resistance. So you can actually, for a raining cloud, the droplet size may be larger than the raindrop which you observe onto the Earth's surface. But in most circumstances, particularly the white cloud, that non-raining cloud that you see, size will be much smaller. Still, what will be the size? I mean, do you have idea about that? What is the size of
The cloud droplet is around 20 microns or something.
Yes, yes. So typical size is of the order of the 20 micron and so on. Okay, that size is more than 1 micrometer, but less than 1 millimeter definitely. Okay, so this is the range of the droplet sizes we are talking about. So for most part of the visible wavelength, if you are talking about, your size parameter will be of this order. Okay, the clouds. So you can, if you are doing these calculations, can actually use the value of q equal to 2. Okay. Now go back to this. So I come back to this equation. I define what is the q. Then I told you that for the typical size of the cloud droplets and the wavelength, visible wavelength, value of the q will be most of time close to the 2. Okay. We can substitute this value into this equation, and we can get a new equation. So our equation is like this: K prime is a cross section, n is a number of droplets per centimeter cube or per meter cube of the air. Delta Z is the thickness of the cloud. Okay. Okay. So if I substitute value of the K prime, now I have made one small mistake here. It's not a mistake actually. I have not mentioned you to the convention. Delta Z is taken from top minus bottom. Okay. So it is taken negative. Sorry, taken bottom minus top. So our tau is positive in that case. Otherwise, variation into delta Z and tau is like pressure. As you go higher the jet, your pressure will be lower. Similarly, your higher the jet, tau will be lower. Anyway, our main point is this one. So instead of K prime, we write the efficiency, extinction efficiency, multiplied by the size of the particle. Okay. Now, why we want to do that? Okay. We want to do that because we know that Q is 2, and then we have a size of the droplet, we have number of the droplet. Okay, so if you multiply, we can get the volume of the droplet. Okay, and we know the density of the water. Okay, we can write rho. So this rho and then the rho which we have. Okay, so here also we have a rho. That rho is different. This rho is not the density of the material. This rho is a concentration into the air, whereas this rho is actually the density of the material. In this case, it is in water. Okay, and what is the density of the water?
1 kg per meter cube.
1 kilogram per meter cube. No, that's not the true answer.
So 10 raised to 3 kilometer per kg per meter cubes.
Sorry, I couldn't
10
get your
raised to
answer.
3 kg per meter cubes.
Yeah, that's correct answer.
So 10 raised
1000
to
kg,
3
1000
kg
kg per meter cube. 1000 kg per meter cube. Okay. But if you are talking about the say ice particles, then this will be little smaller than the one. Okay. Because the ice has a lower density than the water. So what I have done is hello. Can you hear me now?
Yes, sir.
Sorry,
Yes, sir.
my connection was again lost. Can you see the slides?
No, sir.
No, sir.
Yes, sir. Yes, sir. Yes, sir.
Okay. Okay. Yeah. So okay. So what I was trying to say is that I have an optical depth equation, which is this as per definition, and then I have kind of transformed this equation in terms of the mass of the water into a given cloud into a distance delta z. So if you multiply mass and delta z, you will get the kind of an amount of the water or mass of the water into a unit column of the into a cylinder of the unit area of the base. Okay. So, and that is what most of time you can, this is something that you can estimate using the various instruments. It's called liquid water path. Okay. And its units are often kilogram per kilogram of air or kilogram per meter cube of air and so on. Okay. Uh, so M into delta Z is an liquid water path. You should remember that. This term, as far as you do atmospheric science, you will come many time across. Or if it is an ice cloud, then it is called ice water per unit path. Okay. So its unit is uh, uh, weight per meters, weight per centimeter square or weight per meter square. Rho is of course density of the water or ice, whatever the case may be. R is the size of the particle. Okay. So what is the particle? Here, particle is the cloud droplets or the ice droplets. Okay. We could write this equation because we know the extinction efficiency goes to the when where R is much larger than the wavelength. Okay. Or the size of the particle is size of the droplet is much larger than the wavelength of the radiation we are interested in. Okay. So this is true for the visible wavelength. This may not be true for the infrared wavelengths. Okay. So let us do some exercise. Okay. I give you some values, and these are the values we have actually observed into the atmosphere of India. So let us take a three type of the ice clouds. Okay, all of them has a liquid water path or ice water path, 100 kilogram per meter square. Sorry, 100 gram per meter square. but each of these cloud has a different particle sizes. One cloud has a 25 micrometer, another is a 20 micrometer, another is 15 micrometer. I want you to calculate optical depth and tell me. Again, I remind you, what is the ice water path? Ice water path is m into delta z. So writing ice water path, at least it makes you, so you would have required the size of the what is called physical thickness of the cloud. Delta z is a physical thickness of the cloud. So if you multiply m into delta z, you get a quantity that is kind of things you don't. So you, without knowing the physical thickness of the cloud, you can actually know what is going to be optical effect of this cloud. That is the beauty of, that is the reason we use the ice water path, or cloud water path, liquid water path. Okay, so that quantity, so m into delta z is given to you 100 gram per meter square. That is an amount of the water into the atmosphere, into the atmosphere in terms of the cloud, in the form of the cloud. And then I give you the different sizes of the particles. They have radius 25 micrometer, 20 micrometer, and 15 micrometer. And I want you to calculate the optical depth of the cloud. And these are not some random numbers. These are the numbers, actual observation into the atmosphere. So please do the calculations and tell me. Those all of you doing the calculation, raise the hand, so I know that at least you are listening to what I'm saying. Okay, at least a couple of people are doing. Okay, Heath has done a calculation. Heath and Dhani both have got the same answer, 6. For the 25 micrometer. Optical length is 6. Then Dhani has got the optical length for the 15 micrometer, and that is 10. Puja, Kavita, Kusali, all of them has got answer 6 for the 25 micrometer. Avni. $7.5 for the 20 micrometer. Kavita has got that answer. Heath has got 9.5 for 10 micrometer, but I have not asked for 10 micrometer, but fine. I mean, you have done extra work, that's good. Nishal has got the 7.5 optical depth for the 20 micrometer. Okay. Okay, Heath is okay. So for 15 micrometer, your answer is a 10. Okay. Okay. So let us see what answer I have got. Okay. So these are the answers I have listed here. I hope, I mean, are you able to see the numbers?
Yes, sir.
Okay. Anybody has got the answer very different from this one? I mean, you might have got slightly different answer because I have used the exact density of the ice. Maybe little different density of the ice than what you have used. So, but you should have got the answer into this this order. It should not be very different from this one. Okay. And point I want to make is that which one is the largest, which cloud has the largest particle size? Obviously 25 micrometer, the cloud that has a 25 micrometer has a large size of the molecules, whereas a cloud which is an 15 micrometer has a small size of the droplets. All of the clouds has the same amount of the water, but because their particle sizes are different, you are getting the different optical depth. That is the point I want you to remember. That is the point very central to the something called indirect aerosol effect. You will come to know about one of the very challenging topic into the climate science, why we are not able to predict climate accurate, why there is so much uncertainty in predicting climate, because of this indirect effect. Now you have same amount of the water into the atmosphere, but because your particle sizes are different, you have different optical depth. So which cloud will scatter more radiation out of these three clouds?
15 micrometer.
Yes, 15 micrometer will do a lot of more scattering compared to the cloud that has a 25 micrometer size. Okay, because optical depth is 11 here, optical depth is 7 here. Okay, so if you can you keep the same amount of the water, but if you can just reduce the size of the particles, you can do the scattering, you can increase the scattering. I can give you another example. I hope all of you have the fridge at your home. Okay, refrigerator at your home. Okay, you might have seen, if not at home, maybe you have seen the refrigerator at your friend's home. But anyway, so there is a compartment where you can make the ice. Okay, in the refrigerator. If you open this compartment, often you will see the frost is formed into this compartment. Okay, and that will look very, very bright. Whereas if you see the ice cubes, okay, they will not be as bright as the frost that is formed onto the surface. Why? Because frost is made of the smaller particles, whereas ice cubes are large particles compared to, okay. So frost appears very bright. For example, snow appears very bright, but ice appears very not so bright. Okay. Because snow has a smaller is a collection of small particles, whereas ice is a single large particle. So I think we are near the 12:30 end of our today's these things. Maybe let me see if there is something we can cover. Okay, what I want you to do is okay. So we looked at this radiative transfer equation in forms of the plane parallel atmosphere. This mu, the term mu comes from the fact that we are treating atmosphere as a plane parallel. Okay, otherwise that mu will not be there. This tau, both optical thickness and optical depth is people use the symbol tau. So this tau is an optical depth, and the equation is this one. And if you are doing the radiative transfer calculations for upward going intensity or downward going intensity without worrying about the scattering, your solution will look like this. What I want you to do as an exercise is find the solutions for the Earth's atmosphere, assuming it's a plane parallel. We have done already this exercise for optical thickness, not for the plane parallel atmosphere, okay? Not for the optical depth. I want to do this exercise for the optical depth, and you will get the answer that is similar to this one, okay? Then we can take up the scattering. That we will, I think, start next week. So that's all. Thank you. Any questions?
Hello.
Yeah.
Sir, when we are measuring AOD, sir, which approach is best, ground-based or satellite-based? Means in which we get more accurate results?
Just give me 1 second. So I'm just writing down something that I've given you an exercise, because I keep on forgetting what exercises I have given to you. So you have to find the solution to the radiative transfer for plane parallel atmosphere. Okay. Now coming back to the Heath's question, which AOD is better, whether ground or whether satellite-based AOD. Ground-based AOD is much accurate compared to the satellite AOD. The reason is that when you are estimating the satellite, when you are using the satellite to estimate the aerosol optical depth, you have to make many assumptions regarding the aerosols. Okay, what is the size of the particles, or what is the absorption property of the particle? Whereas when you are doing the observation from the ground, you don't require these assumptions. We can simply, without assuming anything about the aerosol, you can calculate the aerosol optical depth, and that's why ground-based aerosol optical depth is much more accurate than the satellite-based aerosol optical depth.
Thank you, sir.
Any other questions? Okay, so I will stop the presentation. Yeah, so any other questions regarding from previous lectures or something, that also you can ask if you.
Students, if you have any question, you can ask. Also, you can share the question in the chat box too.
Yeah. Those who cannot speak, I mean, they have difficulty with the thing, they can write in chat box. Even they can send the question by email also, that's all right. What actually I want to do is that it is going to be a complicated exercise, but you can actually take the photograph, okay, and then find the extinction coefficient using from the photographs using your mobile phone or something like that. That would be the truly what is called experimental physics, experimental atmospheric physics. And then you can compare the value with the nephelometer values that you have at your institute.
I think that there is no further question, so you can complete the lecture.
Okay. So nice talking to you. We will meet again next week. Thank you. Thank you and
Okay,
goodbye.
sir. Goodbye, sir.